welcome everybody. Today I'm very happy to introduce Guilherme. He did his PhD in Princeton, then he moved to University of Amsterdam and University of Leiden, and now he's a professor at the Scuola Normale Superiore in Pisa. He works with many aspects of cosmology, and today he's going to tell us about decoding primordial fluctuations. Thanks a lot, Guilherme, for accepting our invitation, and please, the word is yours.
All right. Thanks for having me. Can you hear me okay?
Yes.
Okay. All right. Okay. So what I want to tell you about today is a bit about what we understand about the beginning of the universe, the initial conditions of the universe, what we would like to learn more about what happened back then, and mostly the theoretical challenges that we have to. I'm getting some feedback. Is there? Okay. So mostly the theoretical challenges that we have to address in order to make progress in understanding what happened at the beginning of the universe. So yeah, by the way, I encourage you to interrupt me at any times and ask questions. So I'll start with just a little drawing and a timeline of our universe. So our source, so here we are, and we observe from our past light cone, from cosmological observations, all sorts of things about the universe. We see stars, galaxies. We can see even the cosmic microwave background radiation at very early times. And this distribution looks random, but the point is that in the statistical distribution of structure in the universe, you can read off essentially almost all of what we know of our cosmology. So just to illustrate this point, so we observe from our past light cone all sorts of structures. So for example, we observe like galaxies. Sorry for my poor drawing. These are galaxies all over the sky. And there is some large scale structure of the universe. LSS stands for large scale structure. And the matter is clumped and distributed randomly. Then there's a whole period in which the universe is actually just made of gas. There's no structure that's being formed. So time goes upwards here. So there's some dark ages of which we know very little. And then at some point, we have information from this fossil of the very early universe. We have, unfortunately, I don't have color chalk, so you have to imagine it with me. We have like a snapshot of the universe, the form like of a bath of radiation that's fairly homogeneous, coming from all directions. This is in microwaves, so it's cosmic microwave background radiation. And this was emitted when the universe was around, roughly speaking, 300,000 years old. And that's pretty much right now the farthest that we can go back in time. Okay? So here is at least the old picture, the hot Big Bang. So when we keep pushing the clock backwards in time, this is when the clock stops. And the CMB again has, just like we have structure, we have galaxies and so on distributed in the sky. The CMB also has a distribution of hot and cold spots. So some spots are a little bit warmer, some spots are a little bit cooler. So I'm trying to represent it with like filled spots and blank spots. So we would like to understand, infer cosmological information about the universe from this statistical distribution. So one thing that turns out to be very useful to plot, for example, is the correlation function. So if you look up in the sky and you fix some angular separation in the sky and measure the temperature fluctuation point A, temperature fluctuation point B, you take these temperature fluctuations and you multiply the values. Okay? So there is some average temperature of this cosmic microwave background, and there's some temperature contrast, which is the temperature at your given point in the sky minus the average temperature of the CMB. And then this, of course, depends on position. Then you can average in the sky as a function of separation. Okay. So you fix the separation, take all the points at fixed separation and multiply the fluctuations. For example, technically you write this plot as a function of multiples because it's kind of it's a spherical distribution of radiation. And you get as a function of the multiple, you get like some very beautiful plot that has these acoustic peaks, and then it goes up and down, and the signal starts being damped. So if I go in this direction in the plot, then here I'm looking at small separations in the sky. So large L is like small angular separations in the sky, while small l, as I go in this direction, I'm looking at wide angular separations in the sky. So there's a ton of structure here, and very importantly for us, there are correlations. It's not zero for all values of L, including very wide angular separations, okay? So you learn that the temperature map, even though it looks randomly distributed, it's widely correlated. The same thing is true if you look at now here, it's a different type of proxy of cosmological information, but then you would look at the density contrast. So you would plot sort of density contrast normalized by the average density of the universe. There's a 2-point correlation function as a function of a wave number or a separation in the sky. Okay, so now this is a 3D map because you can do this map at various redshifts. And again, it has some interesting structure. It goes up and it goes down. It has small wiggles and so on. And these plots essentially tell us a lot of what we know, pretty much everything we know about the universe. It tells us about the duration of the radiation-dominated era, the duration of the matter-dominated era. It tells us about the existence of dark matter. It tells us about the existence of dark energy. So we fit the cosmological parameters by trying to fit these curves. And the amazing thing about the standard model of cosmology is that you fit all the curves with a handful of parameters. So the standard cosmological model is called lambda CDM, which stands for cosmological constant. So there's some dark energy component. The universe is undergoing accelerated expansion as we speak. That's what lambda stands for. We need some vacuum energy at the moment. And we have cold dark matter. We think the galaxies are clumping around these big halos of cold dark matter. And importantly for the talk, which is really the focus of my research, is the question of initial conditions. So it's not in the name, but it's as big a part of the standard model as the component. So it's not that we just have matter, ordinary matter like us, stars, galaxies, and cold dark matter and dark energy. We also have special initial conditions. So, and how do we characterize that? If you go to the hot Big Bang, to the very beginning of the naive beginning of our of this hot plasma that is cooling down and forming structures and so on, then you can characterize the gravitational potential statistically, because there must be little seeds of gravitational wells and gravitational peaks. And around the gravitational wells, matter will clump and form structure. So that's how we think structure comes about. So the original gravitational potential at the hot Big Bang is not uniform everywhere. So there are preferential points around which structure clumps, and that's why we form these inhomogeneities in the CMB and in large-scale structures. Okay? So the way to characterize this at the level of the initial conditions is, maybe I'll just move here, but it's related to what's happening here. We would like to characterize now on this surface, so it's a fixed time surface, but I need to know the gravitational potential like in all points in the sky. So as a function of separation in the sky, or more technically, as a function of wave number, I would like to write a plot of the statistical distribution of the gravitational potential. This is a variable that we call zeta, and maybe in a few minutes from now, I'll define carefully what it is. And it has a 2-point correlation function that turns out to be very simple. So it's almost scaling invariant. So if you were a scaling invariant and I multiply this 2-point function by k cubed, it would just be a constant. This k cubed is just coming from the fact that we're in 3 dimensions. So if you Fourier transform scaling invariant 2-point correlation function, you will get 1 over k cubed. So if you multiply by k cubed, you get a constant. And it turns out that even from the data, we can tell that it's not exactly constant. There is a small tendency for you to have slightly less power at small scales. So the correlation between the gravitational potential at different points is slightly smaller at short scales compared to large scales. So the amazing thing about cosmology is that we can fit for these two numbers. One number that controls, if you wish, the overall height of this curve, and another parameter that controls the slope. If you parameterize this, for historical reasons, you write ns minus 1, and the cosmological parameter is called ns. But the point is that this is a small number. So ns is close to 1. And this is a number that you fit from the data. So for example, when you hear that the cosmic microwave background fluctuations are of 1 part in 100,000, this is a typically quoted number. So it means that the CMB has an average temperature of around 3 degrees Kelvin. So the hot spots are maybe 3.00001, 401, and the cold spot will be 2.999999. Okay, so those are the types of fluctuations that we're talking about. So it's a typical size disorder 10 to the minus 5, and this number is more or less directly correlated to these fluctuations. So in fact, from the data, we know that AS is order 10 to the minus 10, just because you multiply 2 times 10 to the minus 5. And this ns minus 1 is order 10 to the minus 2. So this is really all we know from observations. From observations. For example, most recently from the Planck satellite. We know these numbers with kind of exquisite accuracy, and this is the order of magnitude that we get. Okay, so this is all we really know from observations, at least at the level of detection. We know that we need these very special initial conditions imprinted right at the beginning of the universe. So that, of course, raises a puzzle. By the way, are there any questions up to now? Or?
I may have a question, if I may.
Yeah.
So just a naive question, why, so when we look at, for example, temperature fluctuation correlation, so why the, well, it seems like larger scales are more correlated at smaller scales. So the largest maximum, as the way you draw it is for
this peak here,
yeah,
you mean?
for the smallest multiple, right? So that's larger scale.
Yeah, so for the smallest multiple is a bit smaller because these are such wide angular separations that the universe is so young, there hasn't been enough time for them to have any sort of, they're essentially frozen. So from here, you already get a hint that you need almost scale invariant initial conditions because you're looking at such wide angular scales that there hasn't been enough time in the age of the universe for the plasma to really feel the presence of these long-range correlations. Okay? Now, the physics of the oscillations is because you have a plasma, a hot plasma from the hot Big Bang, and you sprinkle around these potential wells. It's like throwing rocks in a pond, so you start having acoustic oscillations. So at the beginning of the hot Big Bang, you have like a homogeneous plasma sitting on top of these bumpy gravitational potential. And then, yeah, it just starts feeling that there are some valleys and some peaks, and it undergoes acoustic oscillations. So this is literally you see visualizing the acoustic oscillations, so the plasma waves traveling throughout the first 300,000 years of the universe. So that's where the physics of the peaks comes about. At some point, the multiples start decaying because of some other effects of related, roughly speaking, to the thickness of this surface for when they actually the universe cools down, and then the photons can start free streaming towards us. But it doesn't happen uniformly everywhere, and it washes out some short scale fluctuations. So that's yeah, there's a ton more. I mean, you can take a whole course about decoding the physics of this curve, but I think for the purpose of this talk, this is more or less what you should keep in mind.
Sorry, I may have an even more naive question from remote, which is, do we have any idea where this bumpy gravitational field comes from, or
yeah, that's where I'm going.
Assumption?
No. That's the whole point of the talk, if you wish, to explain how come you have these correlations. So I just wanted to start by reviewing what we know, and then I'll try to explain our current idea or paradigm for how to relate these numbers. And this is why I'm going to use two blackboards. That's
Okay,
exactly where I'm going. Yeah.
Thanks.
Very good. So this is the right question. So it's kind of a big puzzle, right? You have these correlations. They look acausal. They are imprinted right at the beginning of the universe. So it looks a bit strange. And the solution that we think is the correct one is that actually this is, even though this is as far as we can observe, here backwards, it really depends on our modeling. But it comes really from the standard model, just continuing pushing this plasma backwards, plus initial conditions. And then what gives rise to the initial conditions themselves? And then, so we think that the timeline goes further down, backwards, and that there was actually an earlier period in which the universe undergoes accelerated expansion. So the cartoon, something like this. So the universe looks very homogeneous now because the part that we can actually observe was a very tiny patch. So there was a ton of causal contact down here at the neck Of course, we don't know how this thing actually starts, and if we can access what happened back then. But once you assume that this exponential expansion gets started, then you can explain all sorts of puzzles of the old picture of the hot Big Bang. Okay, so here, down here, it's still a big puzzle how this process gets started. But once it gets started, and this is what we call cosmic inflation. Once it gets started, then I will give you some good news. So cosmic inflation was really designed to explain why the universe is so flat and so homogeneous. It's just the picture that if you have a phase of the universe which undergoes accelerated expansion, then you just stretch out any early timing homogeneities and you end up with a very flat, very uniform patch. And then, of course, you need to stop inflation and make whatever is feeding this accelerated expansion heat up the usual particles of what we observe in the sky. We don't know the field that gives rise to this accelerated expansion. But then once this transition period is achieved, then you're good to go. So this is what the idea was designed for in the early 80s. But then there's a beautiful consequence of the idea, which is that you can't achieve perfect accelerated expansion everywhere because of quantum mechanics. So there's some intrinsic uncertainty in how long the acceleration will last at different points. So even though you're trying to stretch the universe in all directions and kind of wash everything out, you're not perfect everywhere. So you end up with some small inhomogeneities here and there. It's inevitable consequence of quantum mechanics. But not just that, the kinematics of this era is such that you get exactly almost scaling variant initial conditions. So it explains why you end up with these long-range correlations that are almost scaling variants. So the physics of what's going on is that if you think of the gravitational potential as some sort of particle, if you had uniform gravitational potential everywhere, you would just have like some fields that has a very homogeneous value all over the place. And then if you think of the fluctuations as excitations on top of this fluid, then I can draw a picture that looks like this. So you have quantum mechanically, you have a short range fluctuation, just some quantum mechanical fluctuation of the vacuum itself. And then because of accelerated expansion, these two particles, they get pulled apart. So it's the same physics that you're used to if you study, for example, polarization of the vacuum. So if you apply an electric field on the vacuum, when we learn about quantum electrodynamics, you apply some electric field on the vacuum, and then electron-positron pair will generate some interesting vacuum polarization, so some quantum mechanical effect. So this is what this diagram here is representing. So this is very short-lived because you're producing a pair, so you need to give enough energy out of nothing to these two particles so that they can propagate. You can do that quantum mechanically, but because of the uncertainty principle, it can only last so long. So for a very short time, this is possible, and then they quickly reannihilate. Okay? So here, naively, if you were in flat space, it would be exactly the same diagram. You would have like a formation of a vacuum polarization, and then these particles would quickly reannihilate. But now, because space-time is expanding, these two particles are pulled apart, and they actually never reannihilate. And they end up leaving some physical imprint at late times. Okay? So this is the physics of how we think the initial conditions come about. The initial conditions, so the conclusion of this exercise is that the initial conditions are, we believe, vacuum fluctuations during inflation. I think this is pretty cool because it's exactly the same physics of this type of vacuum polarization diagram, but because you are in curved space, this has like a very fundamental consequence that it's essentially where all the structure comes from in the end. We hear, like, even poets talk about the fact that we're made of stardust, that is the heavy atoms are produced in the cores of supernovae, but maybe even more philosophically appealing is that structure is made of tiny quantum fluctuations that get stretched to astronomical separations. That's the picture. And the kinematics of this era, so cosmic inflation is well described by a quasi-de Sitter phase of the universe, so some background cosmology that in which the universe expands exponentially fast. It has a lot of symmetry, and one of these symmetries is exactly the symmetry responsible for this almost scaling variance that we observe in the data. Okay? So that's the conclusion. That's where we think these two numbers come from. So what else can we learn about these? If we take the paradigm seriously, what else can we learn? Right? So here I drew like the simplest possible process, which essentially gives rise to this correlation function. It's kind of like free propagation of a pair of particles. So you need this quantum mechanical fluctuation to be produced. That's where quantum mechanics kicks in. But then after they're produced, they're free stream, which is kind of can be taken into account semi-classically. And technically, you can just see it by quantizing kind of like the small fluctuations in the leading order approximation. So it's like a free field theory for the experts, but in curved space. Okay? So how would we learn more about what happened back then by studying these types of maps of the sky? So let me make an analogy with particle physics. So in particle physics, we learn about what's happening at short distances microscopically by essentially smashing particles one into the other. So we learn about microphysics by probing shorter distances, and we can probe shorter distances. Like the microscope that we have is essentially scattering. Okay? So we take bundles of particles, like the ones that are prepared at CERN. They are like smashed into each other. They come very close for a very short period of time. They exchange new particles. We learn about new forces. And then this stuff is scattered all over the place and leaves an imprint in the debris of the scattering. Okay? So what we really learned about here is that there is some particle that free streams. It's quantum mechanically produced efficiently during inflation because it gives rise to these initial conditions. But we haven't learned about what the particle is made of. How does it interact with other particles? Can we measure other particles? So if we push this analogy, we would like to study the analog of scattering in the case of this cosmological setup. So that's the direction that I'm going to go to. So are there any other questions or? So so first of all, one motivation is we just want to understand microscopically what's happening in this early phase of inflation. There are many interesting aspects to this problem. One is that we are inferring that there was causal time evolution, and then there's some causal way of generating and imprinting these fluctuations that they look mysterious. If I forget about this part of the board, it looks very mysterious because I can explain the data by this curve, but then there's correlation right here at the naive t equals 0 of the universe. This doesn't look too satisfying, and now we have some sort of explanation that there was some causal, like short range correlation that got stretched out, and then all we really need is a scalar field that will be converted into this gravitational potential. Okay, so that's really all we know, but we don't know what the scalar field is made of. We don't know how it interacts with other particles. We don't know if we can use it to learn about other particles in our universe. And I'll try to convince you that in principle we can, and we have the theoretical machinery to start attacking this question, and we have the potential of observing the types of interactions that I have in mind in future cosmological surveys. So the first thing, yeah.
Sorry, Guilherme, I think there is a question by Edson. I think, please.
Just a question. Why would be necessary a scalar field and not other field? I mean, is there any reason for being a scalar field?
Yeah. So this curvature fluctuation is a scalar fluctuation, and intuitive way of understanding why it must be a scalar is because if it's scalar, you can generate like a spherical wave around which then stuff easily clumps. If I have, for example, tidal deformations or deformations that pick a direction, like vector or tensor fluctuations, then it tends to not just clump but spread stuff around. So it's not efficient in generating structure in the universe. Okay, so that's essential.
But then the other fields would come from the scalar field. The other fields, gravitational field, for example, electromagnetic field.
You can generate all sorts of other higher spin fields from the scalar field, but we don't know how this scalar field is. All we really know is that this scalar field sources the gravitational potential at the hot Big Bang. But then you need to actually form the plasma of particles, of photons, of standard model particles. And the picture that we currently have is that this scalar field just dumps all of its energy into the particles of the standard model. We don't think that it's currently active. Okay? There are some people that speculate that maybe this scalar field is the Higgs particle, but it's one possibility. You need to model build to make it work. So we don't really know much about the scalar. All we really know is that it must be active during inflation to generate this curvature perturbation. If you try to generate the curvature perturbation out of higher spin fields, then it's not efficient. You won't be able to get the scale invariant power spec 2-point function.
Okay, thank you very much.
Okay, so yeah, maybe one technical thing to keep in mind is that the measurement of this number here is related to the mass of the scalar field. Okay, so roughly speaking, not so roughly, like the ns minus 1 is roughly related to the mass of the scalar field. Let me call it phi, whatever that scalar field is. And it's a dimensionless number. So mass in what units? It's the mass in the units of the expansion rate of the universe. It's not our current Hubble expansion rate, but in the expansion rate of the universe back then. So what we know is that this number must be much less than 1 and roughly order 10 to the minus 2. So all we really know is that we have a very light scalar field around, which comes with the usual puzzles of having light scalar fields in particle physics that kind of motivates a lot of, for example, electroweak physics, understanding where the light Higgs comes from and so on. So that's, yeah, so again, there is an intrinsic acceleration rate of this era, which is controlled by the Hubble parameter during inflation. If I'm start to get a little bit more technical, the metric, I write the line elements. So this is the line element of homogeneous cosmology. I'm going to assume that the slices are flat. Then A of t is roughly speaking e to the ht. So this is the h that I'm talking about. We haven't measured, we can't tell h directly from the measurement of this number, but there's another number that we're trying to measure now that would give us direct access to h. This other number is the measurement of another 2-point function, which is the 2-point function of tensor or of fluctuations. So, you know, this is a background metric. As we know from gravity, there is like a 2-index object, it's a tensor. So there will be fluctuations of the metric itself. And that gives rise to a very interesting 2-point function of primordial gravitational waves. So the whole universe is contorting and distorting itself. And we would like to measure not just the amplitude of the scalar waves, but also the amplitude of the gravitational waves. So if I call them gamma, the gravitational waves, by the same mechanism, we think that it's almost scale invariant. It's kind of a kinematical thing as a function, but it will have some amplitudes. This amplitude is, let's call it AT, because this AS is the amplitude of scalar fluctuations and AT the amplitude of tensor fluctuations. If we measure AT, I'm not explaining this to you, but just take my word. If I measure AT, then we have kind of direct access to Hubble. And we have direct access to Hubble in units of the Newton constant or the units of the Planck mass. Okay, so AT is roughly related to the square of this quantity. So this has the remarkable consequence. So we're trying to measure this. And in the next decade or so, there is a fighting chance that we'll measure this. So if we measure AT in the next 10 years or so, then H is huge. And H is something like 10 to the 13 GeV. So if you don't come from this area, it's like, I don't know, 10 or 1 billion times the LHC energy range. So imagine that nature is giving to you some phenomenon that stretches the whole universe that is done at some average energy density. If you study the average energy density of the universe during this era of inflation, it's also controlled by this energy scale Hubble. And so you have an average energy density everywhere that is like maybe 1 billion times the energy scale of the LHC. You're like 6 orders of magnitude away from the Planck scale. So you're starting to get closer to the Planck scale than you are to energy scales of humans or of astrophysics. Okay? So that's pretty exciting, because then you can imagine that all sorts of interesting new physics can be produced efficiently here, because you have a very high energy density environment. And then our job is to, from measurements of these cosmological correlations, to try to infer if there was something new and interesting going on here. Okay? So let me explain how that works. erase this. There are any questions meanwhile?
Well, I guess I have a question. Why H hasn't been measured so far? Or
Because
I mean,
the parameters that we have, AS and NS, give H in units. They are not units of, they're units in some unknown ruler. We need more measurements to cleanly detect H. And an interesting thing about these tensor fluctuations is that, they're kind of robust. You can't model build the scale that measures the size of their 2-point function. The scalar fluctuations, you can model build the ruler. So it's a dimensionless number. It gives you H in some units, but you don't have access to the units directly. For the tensor fluctuations, you kind of, the ruler is kind of forced on you. It's a G Newton, just because it's coming from the Einstein-Hilbert Lagrangian, same Lagrangian that gives us ordinary gravity. So that's why you need to measure gravitational waves to measure H directly. I mean, there are some plausibility arguments. The reason why people are hunting for these gravitational waves, well, first of all, is because they can. There is the possibility of doing better, of measuring their 2-point function from the data. But also there's some plausibility arguments that AT should be kind of related to the numbers that we have measured. So if you, there's some, this is very vague, okay? Vague, but plausible. The idea is that AT over AS could be order of NS minus 1. And we have measured this, So there's some, in fact, well, if you remember the bicep claim of having measured this number, around 2014, there was a claim of measurement of this number, which turned out to be from astrophysical sources, not primordial. But this realized this expectation on the nose, which is why people were very excited originally. So right now, it's clear that it's less. But if it's much, much less, then maybe we have to revise a bit the simple picture of inflation. And we're going to get better at measuring this ratio, the tensor scalar ratio, by at least an order of magnitude, if not a bit more, over the next decade. So that's why there's interest, and right, and why, maybe I said too much, but it kind of, the point is that AT is a robust measure of H in Planck units, which you can't mess with. So let me just draw the end of inflation. So for the purpose of the rest of the talk, late times will be end of inflation, like a beginning of the hot Big Bang. And we have these 2-point function that we have measured, we characterized by AS and NS. We would like to measure the 2-point function of primordial gravitational waves. You would have some amplitudes, and even the dream, you could maybe measure the scale dependence. But then you have these, if you measure this, and even if you don't, like typically inflation is extremely high energy, and you have this Hubble that is still an unknown, but we expect it to be very high. So then it means maybe there is the possibility that there are other particles. I don't have a color, but maybe there are other particles around. Let me draw them a dashed line like this. Let me call them sigma. They have mass order Hubble. So they are produced efficiently. So if I have a collider operating at an energy scale, then modulo some factors, I'll produce particles of particles of mass controlled by this energy scale. This could be an extremely heavy particle. but then I don't see its imprints directly because, you know, the universe is expanding. So massive particles, they tend to have their power redshifted away. Just dilution. These guys here, they make it to the end of inflation because they're super, super light in units of Hubble. So if you have particles of mass order Hubble, they are produced, but they don't survive till the end of inflation. But you can imagine now that they are produced for a long enough period that they leave an interesting correlation. They decay into the particles that we actually observe. So, for example, something like this. Then you would measure some interesting correlation function beyond the 2-point function that would tell you about the imprints of this new particle. So as you can see now, I have a 4-point function that is just not going to be given by the product of the 2-point function. So it's not a Gaussian random process anymore. And so therefore we call this type of thing a non-Gaussianity, which is kind of a very technical name for something very simple and beautiful, which is interactions. So if I see interactions of these primordial density fluctuations, they are non-trivial beyond 2 points, then I'm learning some new physics. Okay? So what type of new physics can I learn? So what can I learn? There are, roughly speaking, few possibilities. So first possibility, I can draw similar diagrams with less legs. I can draw something with 3 legs, for example, but just to keep things simple, I'm going to keep drawing. You might complain, why did I jump from 2 to 4? But I can repeat the story at 3 points. Let me, for simplicity, just jump from 2 to 4, because it will remind you of stuff that you're used to, might be used to from particle physics. So what can I learn? For example, I can learn about self-interaction. So maybe I try to correlate these 4 scalar fluctuations. And during inflation, the whole thing is about causally something happened during inflation, which then gave rise to this interesting correlation along distances. So maybe they had some strong self-interaction at a certain point. So then I'll learn about self-interactions. Or let me contrast that, or I can have a messenger, new messenger particle. And then I can have even like a more interesting, so I can have this, draw like this. If the arch is longer, then I'm looking at longer distances in the sky because things are stretched for a longer time. So there's this kind of fundamental interplay between distances that you look in the sky and when things happen during inflation. So things that are correlated over very long distances in the sky, they were generated earlier during inflation. So I trade the spatial correlations for time evolution. And now, naively, I would say it's impossible to have correlation between these 2 particles that were generated very early on and these 2 particles that were generated much later. But I can have a messenger that mediates this interaction. Okay? And this is kind of robust. You can't just make these scalars interact locally and have this type of imprints in the sky. It's just not consistent with the picture of what we think happened back then. So we think that this type of correlation is kind of a smoking gun. It's like a particle detector. It's a smoking gun of new species. Okay? So without doing the calculation, you can already infer various things. So first of all, if the interaction happens at only 1 point, if it's a self-interaction, then each particle is stretched by the expansion of the universe roughly the same amount, which means that quantum mechanically there will be some, of course, some jittering here and there, but the signal should be the strongest when I look at the four particles being separated by roughly the same distance in the sky. In other words, this signal should peak. It will be some interesting correlation function. It will depend on all the positions of the points, but it should really be, if I look from above now, I put an eye here and look at this surface from above, it should be the strongest when I put all the 4 points on a square. And so the signal should be much bigger than, for example, if I take something like this. Let me. So if I try to create some hierarchy, I take 3 points very close by and 1 point very far away. This type of physics cannot efficiently generate this type of correlation. Okay. So you see, you learn by measuring the correlation and where it's peaked, you learn about different aspects of what's going on during inflation. So we call this type of non-Gaussianity equilateral. Hopefully for obvious reasons now, because it peaks around when all the sides of your polygon are the same. Just because things are generated at a given instant of time during inflation. Now here the story is a little bit richer, and in fact, you start trading where the power is from going from this picture to this picture. Maybe now, depending on it will depend on the it's a particle detector. So it will depend on the data of this particle. So this is a particle sigma, you'll have a mass, and you'll have a spin. So depending on the mass and the spin, in particular, everything is measured in Hubble units. So it will depend on the mass of this particle sigma in Hubble units, and it will depend on the spin of this particle. If I take the extreme limits in which this m sigma is very small in Hubble units, then I can generate very long-range interactions. So then in this limit, I can in fact imprint quite a bit of signal in this configuration compared as the naive equilateral. And okay, this is another type of non-Gaussianity that what people call local. It's very counterintuitive. Why? Please don't ask me why, because I think I'm gonna just generate confusion. So it's I think the important picture to keep in mind is that this is the most, in fact, non-local thing you can have, because you have an extra particle that mediates very long-range interaction between things happening at different times, because it has a large 2-point function. Its mass is small, therefore the power doesn't get redshifted away by the expansion of the universe. Okay? So how do we measure how do you think we'll measure the mass of the particle now, or the spin of the particle? Can we do another question? Can we do spectroscopy if I had access to the correlation as a function of shape of the points that I'm looking at in the sky? And the answer is yes. And let me tell you how to do spectroscopy, and I'll wrap up. So particle spectroscopy in colliders. Particle spectroscopy in the sky. So let's first do a little particle physics experiment. So I'm looking at the debris of some scattering event, some collider. So for example, I have 2 incoming particles and 2 outgoing particles, and they exchange some new states, okay? Let's zoom in here. If I zoom in, I have a Feynman diagram that looks like this. And then I have the mass of this particle and the spin of this particle. So how do I measure? How do I do spectroscopy? So in the case of a collider, I would look at something like the cross section, the differential cross section of the. Fortunately, that has the notation sigma. So let me just write cross section as a function of center of mass energy. So then the cross section would start growing at low energies. At low energies, I would see very little, like very faint imprint of this particle. You would be essentially measuring, I don't have the precision to measure what's going on at very small distances. So then at low energies, I see that the cross section grows, for example, but I really don't have the necessary resolution to see what's going on here. So then this blob just looks like, it's like in the multiple approximation, it just looks like some self-interaction. Okay? So this is at low energies. And then at high energies, I should really see that this particle like can travel like a fairly long distance in the units of my microscope. I should see it very clearly, and it manifests itself in the growth of the cross section. So the cross section will grow and it will decay. The location of the peak of the cross section tells me, roughly speaking, the mass of this particle. And then now I have the option of looking at the results of the collision at various scattering angles. So I can dial the angle between the incoming and the outgoing beam. There will be some angle theta. I can look at the distribution. If I could plot here, I could plot here as a function of scattering angle what's going on. I would see that the signal would go up and down. So there would be some Legendre polynomial type of envelope of the signal peaks around the forward configuration. Then it goes up and down. I hope that this picture is not more confusing than. So this is another axis in which you see that the signal is modulated. So the peak and this curve going up and down will be modulated by some scattering angle. So then, depending on the polynomial that modulates, I'll measure the spin of the particle. This modulating polynomial is some sort of Legendre polynomial. So I don't have these dials in cosmology, but I can dial geometry in the sky. So how do we do particle spectroscopy in the sky? So now I would like to probe some interesting correlation between, say, 2 pairs of particles exchanging another particle. So one good starting point, so I can dial now geometry. So I have a rough measure of geometry, such a way that here I start from the square, and then I kind of squash the square, okay? There's some squashing parameter that controls, if I go in this direction, how much I squash the square. So if all the sides are of equal distance, so then the biggest contribution to the signal will come just from some self-interaction. So it would just come from all the particles interacting for a very short distance, you'd have just some very short range self-interaction, and you can fit the signal by just some power law type of thing. Okay, so you learn about self-interactions, but again, you don't really learn about what's really going on here inside. You don't have the resolution to see what's going on in the inside. Now, as I dial this hierarchy, then in order for any correlation to survive, I'm really trying to correlate stuff that happens at early times with stuff that happened at early times with stuff that happened at late times. So I should really measure the 2-point function of this extra particle. And let me draw the case of m sigma is order Hubble, but slightly bigger than Hubble. So m sigma over h is bigger than 1, for example, 3 or something. Okay, slightly bigger because then the pictures and the physics is very beautiful. So this is what happens. So as I'm squashing, I'm just creating a bigger hierarchy between these times. I'm giving literally more time for the extra mediator particle to travel through inflation. As it travels through inflation, it's like a particle, it's quantum mechanical. It picks up a phase. You know, we know that the particle, its wave function as it travels through time, picks up a phase that the energy is order of the mass. This is just the quantum mechanical phase, e to the I et. And again, as the distances in the sky are telling me about the time separation between these events. So now if I see this, I should predict oscillations. And this is on the nose what you will get. So you'll find that as I squash the square, I'll start seeing the signal is dying because the 2-point function is becoming smaller. You're trying to make this particle do a very hard job of mediating the interaction. It's competing against the expansion of the universe, but then it picks up some interesting oscillation. And the oscillation frequency tells me the mass of the particle in Hubble units. And just to finalize, how do I measure spin? I can squash the square, but I can also decide to fold it like origami. Right? So I keep this hierarchy fixed, and I can take these points and move them in 3D, create some sort of polygon that is cannot be written on the piece of paper. And then again, if I could draw, I'm not going to do what I did here because it was kind of not so nice. If I could draw here another axis with the angle between these two sheets, I would see that the signal is again modulated by some Legendre polynomial. One way to think about it is that if I change the angle, each of the pairs acts as some sort of polarimeter, so I can measure the spin of this particle. You measure its 2-point function, and you see if the polarimeters are lined up, it's peaks, and as I move one polarimeter with respect to the other, the signal goes up and down. That's how I do spectroscopy in the sky.
Can I ask
So,
you a question?
Yeah.
What are you actually plotting along these two axes?
The size of the 4-point function. So,
Yeah, vertical.
It's a 4-point correlation function, zeta x1, zeta x4. So it will be a function of the whole quadrilateral, right? So it really depends on all the arguments, and I'm just watering it down quite a bit. I have enough symmetry to water it down to a function of essentially one variable that controls how deformed the geometry is, or a couple of variables controls how deformed the geometry is.
Okay, thanks.
So I think I will essentially stop here. Let me just summarize. I hope I showed you that even though we don't have direct access to what happened at the beginning of the universe, we have some nice picture that explains causally where primordial fluctuations come from. This picture has enormous potential of maybe probing new physics at very high energies. And I described to you a bit of the recent theoretical efforts in trying to understand how do you leverage this picture of seeing the early universe as a particle collider, how you would measure, in principle, the imprints of new particles, of self-interactions, of primordial fluctuations in the statistical distribution of these primordial seeds. So from the data, we know that these correlations are small, but there are bounds on how strong these interactions could be. But I would say that it's actually very early days of this type of program, because we have a lot more cosmological data coming in the next decade or so. So our statistical power will increase quite dramatically, and I see no reason why we couldn't detect this type of new physics from these higher point statistics. All we really detected is the 2-point function, but in principle, we could detect in the next decade 3, 4-point functions of primordial fluctuations, and then we're laying the ground for how you would interpret these observations. It has a beautiful analogy with particle physics. It has connections to many other areas of theoretical physics that I didn't have time to describe, but I'd say that it's kind of an infant program, lots to be explored, lots to be done from the theory and from the observational side. So I'll stop here, and I'm happy to take more questions.
Thanks a lot, Guilherme, for the talk. So I think we can move to the questions. There is a question by Ricardo.
Hi. So you have done some recent work on bootstrapping correlators of the inflaton, but you haven't talked about this today.
No. Yeah, it's about how you actually compute the diagram. So I didn't, because I thought it would get too technical. But the idea, I can explain the qualitative idea, and then if you want, I can stay a bit longer. I can give you a rough idea of how it works technically. The idea is that this diagram must be consistent with the kinematics of inflation. So, okay, maybe let me just explain quickly the problem. So the problem is this diagram, even though it looks very simple, it's hard to calculate in practice because, the massive particles in the center don't propagate like simple wave functions. It's just technically complicated to calculate this diagram. You can't boost to the center of mass frame, so you need to do time integrals over these two insertions. You can write down some integral representation of this diagram, but you don't go much farther than that if you follow standard perturbation theory. But now you can ask a different question, which is kind of bootstrappy in nature. The question is, I have this diagram here, and it must be consistent with the kinematics of inflation. So it must satisfy a bunch of symmetry constraints. So it's already useful. But it also must satisfy some dynamical constraints, which is this diagram, there are only 2 moments in time in which interesting stuff happens. So these 2 moments in time in which interesting stuff happens is reflected in the singularity structure of the correlator. So in other words, there are many functions that are kinematically compatible with this process, but essentially a unique function that is compatible with the dynamics of what's going on. There are only 2 interesting moments in time at which stuff happens. Let me contrast with particle physics. If I say I was interested in a very simple type of diagram, just tree level in flat space. So I have 2 options. Either it's context-like, or I can exchange a new state. If I'm working at tree level, this is really all there is to it. Then locality and symmetry will pin down everything to me. So symmetry will tell me that the scattering amplitude only depends on 2 kinematical variables. Then locality will come in the facts that this, if it comes from self-interactions, it needs to vanish at low energies. So in particular, I can only write things that are like polynomial in these variables. And now, if I have a new state, then there is only one singularity when this state propagates on shell. So when, for example, in the S channel, it will look like this. There is only one possible singularity. You'll be a simple pole controlled by the mass of this new state. I was calling it sigma during the talk. Let me call it sigma. But there's more kinematics and unitarity that enters in the story, because when I'm sitting on the pole, then I'm allowing this particle to propagate arbitrarily long distances. So then the amplitude must factorize. The residue at the pole must be the amplitude on the left times the amplitude on the right. But there's so many constraints of kinematics that scattering amplitudes in flat space at 3 points are more or less unique, given the quantum numbers of the process. So in fact, you know the residue on the pole, so you can write it down. It will depend on the quantum numbers and the coupling constant. It looks something like this: g squared times some prefactor that I forget times some Legendre polynomial that depends on the scattering angle. And the scattering angle depends only on t. Okay. So this is a kind of a benchmark of what we would like to do. So we bootstrapped at 3 level this scattering amplitude, and it's a benchmark of what we would like to do here. So here, the analytic structure of contact correlators is very simple: power loss, and the analytic structure of exchange interactions is only simple poles. There's some analogous story of the analytic structure of exchange diagrams versus the analytic structure of just self-interactions that only have one interesting moment in time. So that's essentially what the bootstrap philosophy in cosmology gives you. You put in the kinematics of the inflationary space-time. You put in the fact there are only certain times in which there are interesting interactions, and you have enough symmetry and enough dynamical constraints that you can just pin down the answer, pin down the correlation function.
Well, depending on some parameter like the mass of the extra particles.
Yeah, so you'll be a function of the coupling, for example, here, of the mass and the spin, but not just that, but of the kinematics, right? So in particular the momenta of all the particles, so K1 all the way to 4, and we can write down this function explicitly for any mass and any spin. It's also kind of cool because you only do the hard dynamical work once, and then, for example, we didn't know how to get it from the Lagrangian for spinning particles. This type of diagram was a real mess, but you have so much symmetry at your disposal that you can essentially bootstrap the spinning diagram very much like here. So if I erase this Legendre polynomial, this is the exchange of a scalar particle. And to get the exchange of a spinning particle, I just multiply it by something roughly looking like this Legendre polynomial. So there's an analogous story here. It's not a multiplicative operator, it's a differential operator. But there's some differential operator that you can act on the scalar exchange diagram and get the spinning exchange diagram. So you can even get graviton correlators from the scalar correlators and so on. So all of this comes for free once you take this point of view of trying to leverage symmetries and the singularities.
Thank you.
And maybe one last comment, because you asked me a technical question, is even at 3 level, there's still a lot that we don't understand. So for example, if you study 3 level spinning scattering amplitudes, 4-point scattering amplitudes in flat space, there's all this beautiful machinery that makes everything manifest, like little group scaling, and it makes manifest the fact that you can't just write like S-channel type of diagrams that the amplitude necessarily involves some conspiracy of the multiple channels in the amplitudes of like gauge theory or GR. And we don't know how to see all of this stuff in the cosmological setup. So for example, you can study this diagram for scalars, and you can apply some kinematical operator to make one of these legs like a graviton. And you will see that even though it seems that naively you're doing everything according to the rules of the game, that you necessarily put in a small breaking of the symmetries. And the only way to fix the problem is by making the graviton couple to everything in a universal way. So you kind of forced into the equivalence principle to make things fully is isometric. But it's not automatic. It's not as streamlined, not as simple as it is in amplitudes. So it feels that there's still something lacking at tree level for very simple processes. So just to contrast how much better we know how to do this type of stuff in flat space compared to cosmology.
Okay, there is a question by Dimitri.
So we have a question from the audience here. Fabrizio, please.
Hi. Hi, Guilherme. Very nice talk. Even for me that I'm not really an expert on the subject. But my question is related to the initial conditions that you mentioned in the beginning of your talk. I was wondering if there is any relation to this kind of Hubble's constant tension that you measure, you verify that in some experiments, in current experiments, and there is any relation with this tension of this constant and with the kind of initial conditions you consider in order to, I don't know, implement this parameterization of the lambda CDM model?
Right. Let me no. It's the tension is at different eras of the universe. So let me draw a picture, and it should become clear. So that tension is related to the Hubble parameter now that we infer now, which is not the Hubble parameter during inflation. So these are two different Hubble parameters. Notice that the Hubble parameter during inflation is not a cosmological parameter. The only thing that inflation gives you is the amplitude and the ns-1 of scalar fluctuations. So the lambda CDM has 6 parameters. The ones that I focused on were these two, and then there's something related to the amount of matter, the amount of dark matter, the amount of ordinary matter. Then Hubble, but the Hubble today, which you call H0, and something related to the fact that the universe is not a completely transparent medium. And so the problem is that we infer H0 from different probes. So we had this picture here. We have us, and we have the galaxies. In particular, we have supernovae, right? So even in our own galaxy, we have like supernovae, like here, here, here. So the point is that you calibrate the distance to the supernovae, and it's called distance ladder because you take stars nearby, you calibrate how far you are from them, and then you use them to kind of anchor to other stars nearby, and you kind of go on. So from this, you infer H0 by the usual V equals H0d, the Hubble law. Okay, so you just measure the velocity that each star is receding away from you. And then there's H0 as a parameter that enters to fit these curve for the large scale structure and the curve of the CMB. So H0 enters to fit these two curves here, okay? And notice that the photons have to travel throughout the whole universe. They kind of trace the gravitational potential through all areas of the universe to reach us now. So we call this a very early time probe, and this is a very late time probe because it's using stars that are not extremely far away from us. So there is some discrepancy. So from here, we infer another H naught bar, and there is some percent level. So H naught here, I forget, something like 69 is kilometer per second per inverse megaparsec, and here maybe 72. I forget, something like this, or maybe the other way around. 72 here. So there's a percent discrepancy, but the claimed error bars are very small, so that if you do naive statistics, it's 5 sigma. Okay, so the claimed error bars are very small for these two measurements. So we think that there's something in between here. Well, one explanation is that the measurement is not completely under control. A lot of people take that point of view, but assume that there's no problem with the measurements, then there must be some new physics here that explains the propagation of light from the CMB all the way to us, or something around us. And if you want like some cosmological solution of the problem, you need to put in some sort of new physics in between. Some, for example, proposal is something that people call early dark energy. So this is there's radiation domination, matter domination, and now there's dark energy domination later. And maybe there's some earlier phase in which there's a small peak of dark energy. It modifies the propagation of photons and accommodates. It changes the rule from which you infer this parameter such that it accommodates this. So now the problem that I talked about is even earlier. The problem I talked about is about how inflation itself gets started. So inflation, so here is the hot Big Bang, is the end of inflation. Then there's this era of inflation, and we don't know what happened here. What gets the exponential expansion going? How bumpy it was, how unlikely it was. Like, are there other regions that get, maybe there are other regions that like collapse, and other regions that grow like even faster and so on. We don't observe them. So how was this surface from which we eventually get some patch that expands exponentially fast, from which we do our observations, okay? So that's the initial conditions for inflation problem. This is hard to address observationally, I think. It has to be done rather indirectly or from theoretical arguments. Now, the problem that you asked is more related to actual observations, and you can try to address with models that imprint new physics at observable scales.
So thank you.
Okay, yeah, let me also thank you for this great talk, and it's really an exciting opportunity to study particle physics as far as I understand. So my short question is whether you expect to observe standard model particles in this way, to sort of calibrate.
Yes, it will. Yeah, that's being studied extensively. I think it depends on what the inflaton is. If the inflaton is well, one way is that the inflaton is a standard model singlet, and then the standard model particles will appear in loops. And so you could have like in this type of diagram, you could imagine like some standard model loop, fermions of the standard model, and so on. And now here, I think Ricardo's question becomes really important, because we don't really understand the analytic structure of loop diagrams in cosmology. It's kind of a thorny business. You can, again, write down the formula for the time integrals, and people plot them, and they get some curves. And depending on the strength of how the inflaton couples to standard model particles, if the energy scale of inflation is relatively low, then you should really see the standard model again in the sky as some sort of background. So you need to understand this in order to figure out if you detect a new particle, if it's new physics, or you're just seeing again the fermions in the standard model. So this is actively studied, and there is a real possibility that you will see them. But from my, I have a more theoretical perspective on this thing. I'd like to understand the structure, the analytic structure of these formulas. And this I find very exciting because we really don't understand how one loop diagrams work in cosmology.
Okay, so I think there are no further questions. So thanks a lot again, Guilherme, for the great talk, and thanks everybody for participating.
Thanks a lot. Thanks for having me.